Hey guys, welcome back to chapter 17. We're going to start moving into the second half of this chapter. So up until this point, we've talked about reactions and reaction kinetics from the standpoint of concentration and rate. So we looked at how the concentration of the reactant affected the rate of the reaction. But concentration and rate are a little bit ambiguous, right? So if we can manipulate these formulas, so this one right here, if we can manipulate these formulas and give us a relationship between maybe like concentration and time, that might be a little bit more tangible for us, right? So I change the concentration and yeah, it goes faster, it goes slower, but how fast is fast? How slow is slow? We don't really have a grasp of that. A little bit ambiguous. So what we're going to do with this chapter is we're going to take the rate law, the one we've been talking about, and we're going to integrate it with respect to time. For those of you that have a calculus background, this is the same integrations that you guys do in calculus. We're just applying it to a chemistry problem. For those of you that have not had calculus, fear not. You don't need calculus. We're not going to be actually integrating anything. I'm going to give you kind of the result of the integration, and you'll need to be able to algebra through it. That's it. So we're going to integrate this rate law with respect to time, and it's going to produce for us an equation that connects concentration and time. So if I increase the rate, if I increase the concentration, how much time is that going to add to the reaction? If I decrease the concentration, how much time is that going to take away? So we're going to look at this relationship between the two. And then we're going to look at the relationship as it depends on the order. So first order reaction versus zero order versus second order. So each of those three are going to have their own integrated formula. So you'll need to know, like, this is a first order, this is a second order, in order to know which equation to use. And then the last thing that we're going to introduce in this kind of section of the chapter is this idea of half-lives. So you may have experienced half-lives in other classes, but we're going to experience it from the viewpoint of integrated rate laws and kinetics. We're going to see. So here's what I'm talking about with ambiguous versus more tangible. Here's a table, right? So these are CFCs. CFCs are known pollutants in our atmosphere. If we integrate these rate laws, like, yeah, I could tell you the rate of disappearance of trichlorofluoromethane, right? But something a little bit more tangible might be, well, if I have X amount of trichlorofluoromethane in the atmosphere, how long is it going to stay there? So what's more tangible, like how fast it disappears or how long it lasts in our atmosphere? So this is what I'm talking about. We're going to get to like numbers and years and minutes and seconds as opposed to a rate that's like molarity per seconds or molarity per years. A little bit ambiguous. So our answers are going to be like more tangible when we figure them out. Okay. So let's look at a first order. We're going to start with a first order. We're going to do some examples, and then in later videos, I'll do a second order and a zero order as well. So here's an example of a first order rate law. So we had kind of two different ways that we identified rate. So this was our average rate, and this was our instantaneous rate. So this one had to do with concentration. This one has to do more with time. So I'm not going to ask you to integrate or to derive these equations, but I am going to show you very quickly how I get to them. So both of these are equal to the rate of the same reaction. So I'm just going to simply write these two equal to one another, right? So K, concentration of A, equals the disappearance of A over a given amount of time. Okay. Here, we're going to integrate with respect to time. So for those of you that have a calculus background, we would do something like this. Integrate it from 0 to t. And whatever I do to that side, I also do to this side. So integrate it from 0 to time t. If you have that background, go ahead and try it. But we integrate it, we rearrange it, right? And we're going to get a formula that looks like this. So big take home here is you need to know how to identify and utilize this formula. So what we get is the concentration of A at time t equals negative the constant for this particular reaction times t, this t is time, right, plus the natural log of the concentration of A at time 0. So if I know the concentration at time 0, I know how much time has passed. I could then solve, well, what's that concentration going to be in 45 years, 45 seconds, whatever it may be. So something a little bit more tangible and useful. You're probably wondering where this natural log came from. It came out of this derivation here. So that natural log is just a product of the integration, not the derivation, is a product of the integration. So that's where we get that natural log from. It comes from the integration process. As I told you guys before, the only way to determine if it's a first order, second order, third order reaction is with experimental data. So it's either something I'm going to have to tell you because I have the data, or it's something you can figure out if I give you some data. Okay. So how would we determine if something is a first order reaction? We would graph it, right? So we're going to take our data points. We're going to have some sort of time that we take our trial or our data, like so every 10 seconds, every 10 years, whatever. So down here we've got time equals 0, and we count up as we go from left to right. On the other axis, we see the natural log of the concentration of A. So we're going to graph time against the natural log of the concentration of A. If it is a first order reaction and we plot these two against each other, what we will see is we will see a straight line, right? That straight line has a slope value of negative k. And all of this information comes straight from this formula. So let's explore this equation a little bit more. So the equation for a straight line is as follows. Y equals mx plus b. So this y and this x are the data points on our graph. M is the slope, and b is the y-intercept. So if I look at this, my y values are natural log of A, right? My slope is negative k. My x values are time, t for time. And then the natural log of concentration of A at time 0 is that y-intercept. It's where it intersects with it, okay? So the reason that I put this equation into this format is it fits this equation for a straight line, and it tells us lots of really, really good information. So here's our x values, here's our y values, natural log. Our slope is a negative value. And if I knew this, what the slope was, that would be my k value. Now, why is this important or helpful? So let's say you had a reaction and you didn't know what order it was, but you did an experiment. So every 100 seconds, you took the concentration of the reactant. Okay, so at time equals 0, it was 1 molar. After 400 seconds, it was 0.089 molar. After 1,000 seconds, it was 0.048. Okay, so you would take this data and you would throw it into a graph. If you had maybe a suspicion that this was a first order reaction, you might throw into a graph time on the x-axis and then take the natural log of concentration for the y-axis. So how would I get that? Natural log of 0.1, natural log of 0.0971, natural log of 0.0944, so on and so forth. And if I were to plug that in, so natural log of concentration versus time, and it gives me a straight line with a negative slope, that is my indication that this is a first order reaction. Then I can do something crazy like, hey, Excel, can you tell me what the equation for this line is? And we see here it spits out that equation for a line, and now we know exactly what the K value is. So that's one question that I may ask on a test. I may say, here's a table, tell me what order this reaction is. And you'd have to peek over here at the Y values. And if it's natural log of concentration, I'm going to tell you it's a first order reaction. Here's another way that I may ask questions from this chapter. So in the previous example, we determined that this reaction is a first order reaction. And we determined that it has a rate constant of 2.9 times 10 to the negative fourth. If this reaction is carried out at the same temperature, and the initial concentration is 0.0225, what would the concentration be after 865 seconds? So we're going to use this equation for our first order reaction. We're going to use the information given to us, and we're going to be able to calculate what the concentration is after 865 seconds. I'm going to take inventory of what I know, decide what it is that I'm trying to solve for. So I need natural log of, actually I'm not even going to do natural log. I need concentration of A at time t. I need the constant. I need how much time has gone by. And I need the concentration of, it's not A, well, yeah, A, at time 0. Okay. So I have 4 variables here. Somewhere in my problem, they must give me information about 3 of them. So let's read back through. First order reaction, that's how I need to use this formula, has a rate constant of, so that's my K value, 2.9 times 10 to the negative fourth. And the units are 1 over seconds, or seconds to the negative 1. If this reaction is carried out and the initial concentration, so initial concentration is the concentration of A at time 0, before anything has happened. So initial concentration is going to be 0.0225 molar. And we let this react for 865 seconds. So time equals 865. So the only variable that we don't have is the concentration of A at time t, but that's exactly what it's asking for. What is the concentration after this much time has gone by? So that's what it's asking for. All right, so now that I know what I have, we're going to plug this into our equation and chug our way through it. So natural log concentration of A at time t, that's what I'm solving for, equals negative 2.9 times 10 to the negative fourth, 1 over seconds. Clear that that's a 4. Times time, which was 865 seconds, plus natural log concentration of A at time 0. So we would take the natural log of 0.0225 molar. So now I'm just going to clean up the right-hand side of this equation a little bit. So multiply these two numbers together. So 2.9 times 10 times 10 to the negative fourth times 865. So this value ends up being negative, I'm carrying that down, 0.251. Our units cancel, seconds on top, seconds on bottom. We're going to take, so plus natural log of 0.0225. So I'm just going to plug that in my calculator. Natural log 0.0225. And I get negative 3.79. So now I'm going to add those two values together. So negative 0.251 plus negative 3.79 equals negative 4.04. Is that my answer? No. That is the natural log of concentration after 800 seconds have gone by. I don't want natural log. I want just the concentration. I want that value in molarity. So how in the world do we get from natural log to just a value? What is the inverse of natural log? How do we get rid of that? It is Euler's. So an E, lowercase e, I can make that a little prettier. A lowercase e to the x equals natural log to the x. These two are inverses of one another. So if I want to get rid of natural log, I'm going to have to, quote unquote, take the e of both sides. So what that looks like is I'm going to take e and then to the natural log concentration of A equals e to the negative 4.04. Natural log and Euler's cancel each other out because they're inverses of one another, and we end up with just the concentration of A. I plug this side, the right-hand side, into my calculator. So I find my Euler's log. It's typically on the same button as natural log. So second Euler's log, and then I'm going to type in negative 4.04, and it spits out 0.0176. Now this is a concentration, so what is my unit on a concentration? Yep, it's molarity. And then the last thing I always ask myself is, does this make sense? So our reactant has been allowed to react for 865 seconds. Would I expect the concentration to be higher or lower than what I started with? Well, if it's a reactant, I would expect the concentration to be lower. So we started at 0.0225. We ended at 0.0176. That makes sense to me. The concentration went down. I'm going to have another video with another example of a first order, and then we'll build on this. We'll do some second order and some zero order examples as well. I hope you guys found this helpful.